Hello and good day to everyone watching this video. We are from group 2-2, which consists of Mohamed Nasrullah, me myself Shireen Natasha, Wynnie Yong, Mohammad Azry Firdaus, and also Zarifah Zahirah. In this video presentation, we will be presenting about our integrated design project. For this integrated project, it involves 3 of our subjects, which are Reaction Engineering 1, Process Modeling and Simulation, and also Separation Process 2. The objectives of our integrated design project is to convert palm oil mill effluent into biogas by choosing a suitable reactor and operating conditions. And next, we have to develop a mathematical models and simulate the steady state process. Lastly, we also have to purify the biogas in order to improve its quality by using an efficient separation technique.
Hi, I'm Wynnie and I'm going to present about the Reaction Engineering 1 in this slide. So the reactor chosen is CSTR to convert POME to biogas in this project, along with optimal operating condition considering economical and technical feasibility. So the optimum condition to run CSTR is the pressure in 1 bar or 1 atm, temperature with thermophilic range 50 to 60 degrees Celsius, and the pH value 6.5 to 7.5. And the microorganism used in this process is the Stenotrophomonas rhizopilla strain, EP10, and Bacillus thuringiensis strain BCT7112. They are used as consortium bacteria in the process of waste degradation. Next, we are going to talk about process of anaerobic digestion. In the first CSTR, it has hydrolysis and acidogenesis. Since hydrolysis did not occur, so we are going to talk about acidogenesis. Acidogenic bacteria convert the fatty acid, amino acid, and sugars into CO2, H2, NH3, and organic acid. In the second CSTR, acetogenesis and methanogenesis is occur. In the acetogenesis, fatty acid and ethanol will be converted to acetic acid, carbon dioxide, and hydrogen by acetogenic bacteria. In the methanogenesis, methanogenic bacteria convert hydrogen and carbon dioxide to methane. The fermentation of acetic acid produces methane and carbon dioxide. Next, the strategy to maximize the selectivity and yield of biogas with minimize the selectivity of side reaction. So the selectivity is calculated from the formation of desired product over the formation of undesired product, while for yield of biogas, flow rate of the product form, which is methane, over the flow rate of the key reactant that consumed. According to answer, we will decide which compound of concentration will increase and which compound concentration will decrease to maximize the selectivity. The last point of the Reaction Engineering 1 is the sizing of reactor in this project. So we are make some assumption before we are calculating for the volume. The first one, hydrolysis reaction is not occur. Excess water is supplied. CSTR is operating in perfect mixing and in steady state. The conversion of POME to biogas is 85%. So the volume calculated in the first CSTR is 1214.6766 meter cube. And the second CSTR volume is the 19475.7973 meter cube.
So for the mathematical modeling for CSTR for the bioreactor, firstly we start with the overall material balance. The rate accumulation of the material in the reactor is the same as the rate of material in by flow and the material out by flow. So it's meaning the flow rate before in and the flow rate after out is the same. Next, we assume it's a constant amount of material in the reactor, and also we assume the same density in the reactor. Then we do the total mass balance, spatial mole balance, total energy balance for the system. But in our report, we have discussed that we don't use energy balance because there's no energy stream for the reactor.
This is the simulation that we have run in the Aspen HiSys software. We are using 2 CSTR and the operating parameters have been assigned from the reaction engineering 1 part. Our temperature is 55 degrees Celsius with 1 atm of pressure, as well as our flow rate, which is 124.3 kg mole per hour.
So for the mathematical modeling for CSTR for the bioreactor, firstly we start with the overall material balance. The rate accumulation of the material in the reactor is the same as the rate of material in by flow and the material out by flow. So it's meaning the flow rate before in and the flow rate after out is the same. Next, we assume it's a constant amount of material in the reactor, and also we assume the same density in the reactor. Then we do the total mass balance, spatial mole balance, total energy balance for the system. But in our report, we have discussed that we don't use energy balance because there's no energy.
A sensitivity analysis was carried out in order to find out how does these operating parameters will affect the reactor's performance. The reactor's performance is evaluated by using the reaction conversion rate. Based on the graph that is shown in the presentation, for the pressure analysis graph, the conversion rate increases when we increase the pressure. This shows that a high pressure is needed in order to maximize the production of biogas. On the other hand, for the molar flow rate analysis, the conversion rate decreases when we increase the molar flow rate. This shows that the molar flow rate needs to be lower in order to maximize the production of biogas. In conclusion, the conversion reaction rate, which is also the reactor's performance, is dependent on operating parameters such as temperature, pressure, and molar flow rate.
Hello, I'm Nasrullah. Now I will explain briefly about our selection of separation unit for this project. Separation process that we propose is adsorption process and membrane process. For the adsorption process, we choose a pressure swing adsorption unit to separate carbon dioxide from the biogas. This unit requires low energy consumption. We recommended this unit due to its short cycle time when compared to the other technology. However, the core of this unit is the absorbent, not the unit itself. The efficiency of this unit significantly depends on the material of the absorbent. We suggest that this unit will be using the carbomolecular sieve, CMS, acid adsorbent. This is due to the efficiency of the material of CMS for the desorption process. I will also touch on the safety of the unit. Just like many present-day processes, this unit has some degree of potential hazard that must be recognized and addressed. The PSA unit does not need a regular maintenance. However, a consistent failure in the unit system can result in a significant annual revenue loss. Therefore, we come up with some strategies and solutions to prevent this from happening. We suggested to implement upgrades monitoring and also use a better valve in order to avoid any unplanned shutdowns that will significantly affect the maintenance costs. Next, I will have Azry to explain our second separation unit.
For the second part of our separation process, we'll be using a membrane separation unit where it provides further treatment to achieve the most purified biogas. It consists of a hollow fiber membrane that is made from kaolin clay. The separation unit is efficient in such way that it is excellent in removing pollution, it is low in cost, and also low energy consumption. For the safety of the separation unit, all details of hazards and also for the operation unit should be noted and be aware of. Membrane separation unit has high maintenance, hence the condition of the unit should always be taken care of. Cleaning and checkup should be done regularly. A challenge that is faced is caused by precipitation and deposition of molecules or particles on the membrane surface or membrane pores. The solution to this is that ultrasound should be added, as it will help tackle the issue of membrane fouling control. The reason for this is that an ultrasound can help separate the particles that are trapped from the fouled membrane. That is all for our separation process part.
To conclude our integrated design project from reaction engineering 1 part, where anaerobic digestion occurs by using 2 CSTR with 3 stages of conversion, which are acidogenesis, acetogenesis, and also methanogenesis. From process modeling and simulation part, the conversion rate of the first CSTR is found to be 68.4%, while the second CSTR conversion rate is 98.6%. The lowest deviation error of the simulation calculation and the manual calculation are found to be 0.52%. For separation process 2 part, absorption has found to be the most efficient separation technique, followed by membrane separation. We have also included strategies in order to increase the production, which includes better valve and also adding ultrasound for membrane fouling control. That is all we have for our integrated design project presentation. Thank you.